My name is Angelo, and I'm here today to present you my talk. It's Data Science and Machine Learning Cybersecurity, Hype or Reality. And I'm a cybersecurity data science tech lead in the data security team for Mercado Libre. Mercado Libre is the largest e-commerce platform in Latin America, and it provides a great environment for buyers and sellers to make business. If you want to know more about me, please, you can follow that link. That's going to take you to my LinkedIn profile. And if you want to know more about Mercado Libre, you can follow here, this link. So, great. So today I want to present you 3 use cases in which machine learning and data science were successfully applied to cybersecurity problems. And also I want to focus on breadth instead of depth because I want to expose you to several different techniques and tools in data science and machine learning and how they were applied to cybersecurity problems. And finally, I want to share with you my experience in field notes because that might save you a lot of time in the future and also headaches. Okay. What is data science? So there is no formal definition for data science, but I like thinking about data science as the meeting point for computer science, mathematics and statistics, and the domain/business knowledge to solve data problems. And in particular, in our case today, to solve cybersecurity data problems. So, as usual, we need to have a cat picture in any successful presentation, right? But wait, there will be more. So, is data science for everyone? Let's see. You know, in my original presentation, there was some animations here, so please don't be disappointed. So we get here data science. So data science is data plus science. So seems fair enough. Okay, so no data, no science, no data science. Right? So you must have data to do data science. So this point is related to the data maturity of the company. So we need to have data. We need to have a maturity concerning storage and management. Okay? And the next, science. What is science? So in science, usually what we do, we formulate hypotheses and test those hypotheses. And tests, how can we perform the tests? We need to perform computational experiments. And computational experiments are research consuming. They consume time, processing power, memory, storage, and depending on your cloud provider, this might cost you a lot, really a lot. But here's the trickiest point. You know, this scientific approach has a high degree of failure. But what does that mean, failure? It means that most of the hypotheses we formulate, they will end up being wrong and not useful to solve the problem at hand. And also this might seem negative, problematic, depending on the data maturity concerning analytics for a company. So, okay, so let's answer that question. So is data science for everyone? Well, it depends on your data maturity. If your data maturity concerning storage, data storage, management, and analytics is low, so no, you cannot. You cannot have cheeseburger. And what if it is medium? Like you have some CM, but you don't manage your data well, and so on. So maybe we can try. I will cook for you a cheeseburger, I'll give you, and then you tell me, yes, I like it. So let's do it again. And if it's high, so definitely you can. Okay. Next. And what about machine learning? What is machine learning? So there is a definition here that is the field of study that gives computers the ability to learn without being explicitly programmed. So this definition is due to the AI pioneer Arthur Samuel circa 1950, and this is a quite good one, actually, and quite up to date because that's exactly what we've been trying to do since then. And next. So if this knowledge is not programmed, explicitly programmed, from where and how will they learn? And by they, I mean the machines. Well, they will learn from data plus learning algorithms. And data is past. You can look at the data as the past experiences. You know, we have the past there, and we want to extract patterns from the past data to try to predict the future. So it's more or less that this is the idea. And learning algorithms. And learning algorithms, they make this possible, to extract those patterns and learn with them. Okay, so here we have an example of a classification problem, and we are using a supervised learning algorithm to solve that problem. So suppose that you want to build an app, and then you point that app to a cat or to a dog, and the app answers, this is a cat, this is a dog. Okay, so this is called classification problem. How can we solve that using machine learning? So first you need to build what we call the training set. This is a training set. What's a training set? Training set is a data set with several instances of cat images and dog images. And most importantly, you need to have a label attached to each image to identify it as a cat or as a dog. Next, we choose a suitable machine learning algorithm for that task. Then we start the process of training, the training process. In the training process, we present the algorithm, a list of image and label. All the images in the training set and their respective labels. And this is the training process. So once the training is done, we want to evaluate the model performance. And to evaluate the model performance, we use another another data set that's called test set. And what is a test set? It's a data set that contains unseen images. And what does that mean? It means images that were not used to train the model, because we want to understand how the model generalized. And from that, we can assess the model performance. If the model has a high accuracy, it means that the model learned how to extract correctly the patterns from the images and to correlate them to the labels. Okay. Now there is a different problem here. And as you can see, we don't have labels. Okay. So here we have what is called a clustering problem. And for that, we use an unsupervised learning algorithm. Unsupervised. And why is that unsupervised? Because there are no labels attached. So it's the machine learning algorithm's job to extract the similarities of these images and put them together into clusters or groups with similar structural patterns. So here we can see that we have only cats and only dogs. So this is the ideal result we expect. And once again, if you want to evaluate the model, we just present the model a test set with some unseen images, and from there we can assess its performance. By the way, this is my cat, okay, Misty. Here there was an animation, okay, and garbage in, garbage out should show up later. But anyways, I will explain. So what's the first step in the machine learning pipeline? So you want to build a project. What's the first step? First step is behind this. It's called problem definition. We need to define the problem. We need to understand the problem. And for that, we need to actively involve the stakeholders, because we need to understand what they want to solve and then translate that to data science project. Okay, and in the end, we need to ask a question that every data science hates. Do we really need data science to solve that problem? Sometimes we don't. And actually, often we don't. Okay, supposing that we need. And the next step is data extraction. We need to understand where the data is. Logs, CM, combination of those, APIs, and we need to establish a way to extract that data efficiently. Next we have a phase that's called pre-processing. Okay, data pre-processing. Data pre-processing, we do cleaning and imputation. Remove noise, sometimes we remove the outliers, and impute missing data. And finally, this first part is concerning data, we have feature transformations. And in feature transformations, usually we do feature engineering. And what is feature engineering? Well, this is arguably the most important step in this data science pipeline. It's where we include business and domain knowledge into our model by crafting smart features. Okay, next. So far we've been dealing with data. Now it's time to deal with models. First thing we need to do is to establish a base model. We need to choose a baseline model amongst several models. Then we need to perform what's called optimization, hyperparameter optimization. And then we do feature selection to choose the features we really need for the model. Okay, so next, we have model evaluation. So what is model evaluation? I showed before, right? We need to evaluate the model using some test sets. And most importantly here, we need to understand how to correlate the model performance metrics to business performance metrics, because the stakeholders, they are interested in these metrics. And us, as a data scientists, we are interested in this. So we need to understand how we can translate, make a translation between them. So model interpretability answers the question, what features affect most of the model's predictions? Sometimes this is a business requirement. We need to know which features are more important and were more important for model prediction. Productionalization. Depending on your company, you can have your internal ecosystem, so you need to refactor all your code that so far we usually implement in a lab environment. So you use your internal ecosystem that could be based in cloud environments or multi-cloud. And then finally, we have the monitoring. What is the monitoring phase? Monitoring phase, we want to keep checking the health of the system as a whole. So we want to check the system resources, like memory, CPU consumption, storage, etc. We want to constantly monitor the model. We want to keep an eye on these metrics to understand if the model is working. And we need to keep an eye on the data distributions, because if the distribution changes, maybe the model stops working. So this is called data drifting. So you need to keep an eye on the model and the distribution of the features. Great. So this brings us to the first case. So the first case, Security Operations Centers, SOCs, receive huge amounts of alerts per day. How to prioritize the analysis of those alerts, the triaging process, to decrease the mean time to detection and the mean time to response. So what we have here is basically a problem in which we want to minimize some metrics, right? Some business metrics. We want to minimize MTTD and MTTR. Okay, how can we do that? So here's a simplified scenario of our problem. We have a CN. The CN triggers an alert. This goes to the SOC analyst. The SOC analyst performs his job, and finally he decides if that alert is a false positive and provides a report, or if it's a true positive and he creates an incident and also a report, and that goes to the incident response team that's responsible to handle the incident, and also in the end, we got a report. So this is the simplified flow of the problem. And we want to optimize this decision-making process here. So let's formulate some hypotheses to help us solving that problem. So the first hypothesis, and the only one for this problem, is prioritizing alerts based on their probability of generating incidents reduces the mean time to detection and the mean time to response. We want to put that hypothesis into test, right? So we need to be the model. And here you can see there is this guy here, this angry SOC analyst. And why is he angry? He's angry because he knows that although he can use this alert level to choose which alert he should handle first, he knows that if he only takes into consideration that information, he's going to end up with a lot of false positives. So he needs to take into consideration this other information about the alert, and we know that usually is overwhelming. So the data science guys kick in and then offer a solution in which we have an additional column here, and this additional column here has a number that represents the probability or likelihood of that particular alert in generating an incident. Based on what? Based on the alert level and based on this other information, and more importantly, based on the alerts that generated and didn't generate alerts in the past. So we need to learn what happened and then associate to this label. And here, so now he's more cool. Why? Because he can just take a look at this number and use that number as the main guideline for him to choose the alerts and quickly review this information as a sanity check. Okay. How can we implement this solution using data science? We need to implement what's called data science pipeline. And the data science pipeline in this case, we have the data extraction, and the data extraction, all the data we needed came from the CM, IT management software for the SOC, and REST APIs. We connected using REST APIs. Feature engineering. So feature engineering is usually useful to ask those questions. You know, who the user involved in the alert, what, the application, origin and destination, when, timestamp of the events, of the alert, how. And how here is related to the user actions that triggered the alert. And how much? So how much inbound and outbound traffic. And there is this very, very important point here. Why? So unfortunately, we can't answer that because data science is not a crystal ball. So we need to live with that, okay? And there is one feature that's very, very important that we came out after some time. That's called content score. And what is content score? Content score is a feature based on the words in the alerts that generated incidents. So we got the alerts that generate incidents and use some natural language processing technique called TF-IDF. It's term frequency versus document frequency to get that score. And we use that information as a feature in our model. So next, we need to perform model development. And for model development, first we need to decide what kind of model we need. And we know we got the past data. In the past data, we have we have the labels. So, and since we have the labels, we have a supervised learning model, and therefore we can use a supervised learning model, And then we need to perform what's called dimensionality reduction. Why? We have this TF-IDF technique, and this technique introduces a lot of features in the data set. So we need somehow to reduce those features because models, usually they they suffer from high dimensionality and suffer from noise when we have a lot of features. So we need some way to reduce. And to reduce that, we can use a technique called dimensionality reduction, more specifically PCA, principal component analysis. It reduces the number of features while keeping the variance high. Next, we need to choose a baseline model. And to choose a baseline model, there is a very nice tool called Lazy Predict that can be used to, actually this tool gets our data set and builds 50 models, I think, from the scikit-learn library and give us a summary of the results using several metrics, performance metrics. And then from there, we can choose the best ones and understand, of course, why they were the best ones. And it turns out that for this problem, we chose the light gradient boosting machines, which is a ensemble three state-of-the-art machine learning method. And then we performed hyperparameter optimization using a Bayesian approach. Why a Bayesian approach? Because there are too many. The search space here is too large. And if we do brute force or grid search or random search, it's going to take a lot of time and won't bring us good results. So we use a Bayesian optimization that is a smarter way to search for hyperparameters. And then you see there is this number here, 80 and 20. It means that we should usually spend 80% of our time doing data pre-processing and feature engineering and so on, and 20% playing with the models. Why? Because of what I showed before, garbage in, garbage out. If this is bad, no matter what kind of model you do or optimization, the results also will be not so good. So please pay attention to that. Okay, using that approach, we got these results. We got the model performance in 3 months in production. We got the precision of 90%, and precision means the higher the precision, the lower the number of false positives. So we got a recall of 80%. So the higher the recall, the lower the false negatives. And we got a F1 score of 80%. What is F1 score? F1 score is the harmonic mean between precision and recall, and show how they balance, how is the balance between them. So actually, if I ask you, what do you want? More precision or more recall? You say both. I want everything. So then we can use F1 score to get the sweet spot between them, because precision and recall, they are two metrics that fight against each other. The higher the precision, the lower the recall, and vice versa. So the F1 score is a good metric to use when we are optimizing our model. And how that translates to business metrics: mean decrease of MTTD, 20%, and mean decrease of MTTR of 15%. Case 2. Case 2, we have this story. So once upon a time, a user used his credentials to make direct requests to some APIs used by a company's app. It worked. Then he created a bot to automate and scale that process. Finally, he created a product based on that data and started monetizing on it. That's a problem. So how can we detect what users are using the bots and consequently the bots? So here we have a detection problem, right? We want to find the bad guys, the bots, and the guys who are using the bots. So again, it's useful to draw a simplified scenario of the situation. So here we have the good guy using the Acme Corporation app, and of course he's using his authentic credentials, get a token, and this is how it should be. Then there is this guy, and he has this idea. Let's reverse engineer the authentication procedure from this app, understand how it works, and using my own credentials, I can, of course, get a token, because I'm a client from Acme and the umbrella, and then I can forward this token to a bot, and that bot can extract huge amounts of information bring that information back to the app. And here we can like provide some products, some reports or some things like that, that Acme Corporation doesn't provide. And then we can basically invite the customers here from Acme, and they pay just a small fee and subscribe to my service. And this guy becomes rich, using data that he can't use. Well, this looks criminal, right? This is a real problem. And how can we solve that? We can detect this guy's in block. How can we detect? So that's the problem that we have. So let's formulate some hypotheses. First one, human user behavior is different from bot behavior. This hypothesis must be true if you want to use behavioral analysis. Second, human user behavior is more diverse than bot behavior. What does that mean? So let's think about that for a minute. You get a bot. What is a bot? It's a script, basically code. What's code? It's a sequence of instructions. We can map that into a graph, for example, a control flow graph. And it's going to be very stable. Now, think about human behavior. Human behavior is a bit more random. Every time you access your app, you do something slightly different. You take more time, less time, you do something before you do some other thing, and every time it's a bit different. So it's less stable. We can try to compare the stability of these behaviors and use it as a feature in our model to try to capture bot behavior and human user behavior. So let's try. Here's an example of behavior, but first we need to define behavior. What is behavior in this context? Well, behavior is temporal sequence of API operation requests made by a user. And here we have some examples of behavior. See, login, gets a balance, transfer, and logs out. We can track this behavior using a table. And this table contains the ID, user ID, the sequences of actions, and timestamps. So from that graph, we extract some almost tabular data, right? Great. So what's next? Well, this is how a behavioral graph usually looks like in reality. Okay, it's much more complicated than my example, but for machine learning algorithms, that's a piece of cake. So fear not about that. Again, data science pipeline. Data science pipeline, in this case, we need to do data extraction as usual. All the data necessary came from the CM. Again, we ask those questions that are very useful for building features. Who, what, when. Here we are concerned about sequences of actions and when those actions happened. How much? So this feature is important. Why? Because frequency is something very important when we are comparing machine behavior and the human behavior. Because machines, as I said, they are more stable, they are more precise, the timing is better, the amount of time to extract information is lower, and people is more random. So maybe we can use that feature as information for our model to decide. Okay, and what else? How much? There is one thing that we want to measure, according to our hypothesis, is that how diverse are the sequences. And to measure that, we can use sequence entropy. And to measure sequence entropy, we can use a metric called channel entropy. Okay, and next, one more question, how much? Now, sequence similarity. We want to somehow compare the sequences. And there are several methods for that, okay? But one method that worked quite well here was this one. It was the DNA sequence similarity algorithms from bioinformatics from a tool called BLAST, Basic Local Alignment Search Tool. And it's fully implemented in the library BioPython. So you see, we got a lot of interesting features there. Yes. And now modeling. We know that we have an unsupervised problem because we don't have the labels. We want to figure them out. The bad guys, the good guys. So what we should do? We should use some unsupervised model to solve this problem. And what we want is to clusterize, create cluster of human behaviors and bot behavior. And after some research, we chose this algorithm. It's called the VDB-SCAN. That stands for Variable Density-Based Spatial Clustering Applications with Noise. Yeah, that's a mouthful. And but actually, it's a quite good one to detect clusters that have variable density and different shapes. So it's a nice algorithm. And then we got each cluster and look within them for anomalies, hoping that those anomalies will represent anomalous behaviors or bots and human beings doing bad things. So it turns out that we got this result. And take a look. These big blobs here, this, it represents human user behavior. And these points in between the clusters, they represent bot behavior. That's very interesting. And it turns out that if we measured, of course, the performance of the model in 6 months in production, and we got a precision of 75%. What does that mean? It means that out of 100 data points that were classified by the model as a positive or bots, 75% of them were really confirmed as bots. So the model worked well. And the business metrics. This model is not in production, okay? It's used to check the data from time to time by the security team. And, but interestingly enough, these results led to a budget approval to redesign the whole security mechanism of the APIs and the apps, taking into account these modern adversaries. So it helped the architecture and the blue team to build a better model, a better application. And case 3. So case 3. We have here a problem about data exfiltration. So preventing data exfiltration by internal users is a key problem in cybersecurity, but also a very interesting one from the data science perspective. Again, how the user behavior could be used for that purpose. We have a detection problem again, right? We want to detect what users are exfiltrating data. And so this is a detection problem. Again, let's take a look at simplified scenario of this problem. We have a user here that in principle he was not black, okay? He was white. And then in the end he changes. So imagine this is white. And then we have this behavior profile. This is what we want to build, behavior profile. And this behavior profile must contain activities and data usage because we are concerned about data exfiltration. So we need to have data usage. And out from this activities and this data usage, we want to find anomalous activities and anomalous data usage. And then we want to correlate them somehow to find for possible data exfiltration cases. So that's the idea. Let's formulate some hypotheses. So the first hypothesis, the normal activities of a user differs from his activities when exfiltrating data, and the normal data usage of a user differs from his data usage when exfiltrating data. So it's what we draw here, right? I want to find anomalies in the user activities and data usage, and then correlate them somehow so we can find data exfiltration cases. Here we need a more comprehensive definition of behavior. We need to add more information there. What can we do? We can define behavior now as a temporal sequence of tuples, as a list, like API operation requests, inbound data, outbound data, origin and destination. They are all useful to detect data exfiltration, okay, made by a user. Here we have the behavioral graph, as I showed before, and now this table has the data related to this behavioral graph, but also takes into consideration some other variables. They are all sequences. All sequences. Sequential data is very, very powerful to detect behavioral anomalies. So we should take them into consideration whenever we try to do anything that is related to behavior. We have the data science pipeline for this third case. So as usual, data extraction. Again, all the necessary data we needed came from the CM. So you want to do data science in cybersecurity? Yes, please, if you don't have a CM, you should get one. Okay, they are very, very rich sources of information for cybersecurity and data science projects. Feature engineering. So feature engineering, usually we start asking those questions, right? What user was involved in that situation? Also, the entities we are dealing with, like the sequences, all the sequences we need to take into consideration. Timestamps, when those events happened. This is important, very important, because think about order in time of some event. You know, if we do something in a different order, our purpose can be completely different. So it's very good to track when the events happened and what happened in that particular moment. And how much, of course, data usage here is crucial. What else? So model development. In model development here, we should ask a question. So what's the question? The question is, how likely is a given user plus user action plus data access pattern? We want to understand the probability of that action happening, right? If it's rare or if it's common, and you want to measure it. And for that, we need to do this, okay? It's called a model. We need to model the joint probability distribution of this scenario. And for that, we can use a method called Markov Chains, which is a probabilistic stochastic model. It's a very old one. It's a very simple one, but it's very, very powerful and underrated. Okay, nobody likes it because it's too simple. People like a lot of fancy methods, you know, deep learning, all that stuff. Forget about that. Forget. And out from this Markov chains, we'll get a bunch of vectors, 6-dimensional vectors, and we will look for anomalies there in those vectors using anomaly detection algorithm called isolation forest. So how likely is the behavior? Actions plus data usage. Let's see. We know that every time the user does something using the app, several graphs are generated. We saw before. So we have a user activity graph, we have a user inbound data usage graph, outbound, origin, destination, and timestamp. So we have 6 graphs to track. And we want to extract information from that graph, some useful information for our model. So in order to do that, we can use the Markov chain. So what is the Markov chain? So let's ask Mr. Markov. So Markov Chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state of the previous event. So it's a very, very simple stochastic model that assumes that the events are independent. So let's imagine that this graph is this one, okay? But here's like in a more pretty format. And each node represents one action, user action, and each transition represents the probability of the user transition from one state to another. So for example, this one could be login, and this one could be like check the balance. If a user does that several times, the probability, this transition probability is high, right? So it's a way to connect the events and their probabilities. It turns out that each graph can be represented by a matrix. And this matrix is called transition matrix. Now what's more interesting? More interesting is that we can infer this matrix from the data, from the training data. So we can get the training data, the past data of that user, the behavior, his behavior, and then we can build out from that the transition matrices for each user. And we are building 6, right? One here, another here, and the other measurements we have. So how can we use that? So whenever the user performs some action, he will create these graphs, right? And these graphs, we can just feed it to the Markov chain, and the Markov chain will output the probability of that event, of that action. And since we have 6 transition matrix, in the end we will have 6 data points, 6 one-dimensional data points that we join, and we have a 6-dimensional data point or 6-dimensional probability space. And then we need to look for anomalies there using, for example, the isolation forest algorithm. And that was the solution. So we have here some data science and the business metrics for this case. In 6 months in production, the model achieved 70% of precision. So you remember, precision is higher the precision, the lower the number of false positives. And how this metric is translated to business metrics. So several attempts of data exfiltration were identified and interrupted, because sometimes the user is exfiltrating a lot of data, so we have time to detect it and interrupt. It's really, really hard to make this thing work in real time, okay? If some vendor says you, buy my tool because it's possible I'll detect this data exfiltrations real time, don't believe him, okay? Don't believe. You show me proofs. No, I want a proof. I want evidences. Yes, and to this day, the model is in production, alive and well, helping to detect data exfiltration attempts. So it's not showing there, but I said, merci beaucoup, thank you very much, muito obrigado. And if you have some questions, I'm here to answer.
Okay, I'll take 2, 3. Oh, you guys want me to run? No, it's too much time. Thanks. What would you recommend someone who has security experience but knows absolutely nothing about machine learning, data science to get started? Because I once took a course of machine learning. It was very math, no application, but from the other side, you don't want to just run random models without having a clue of what you're doing, right? So how would you recommend starting?
So to get started with machine learning, I really recommend you to first take a good course in mathematics and statistics. Okay, there are several courses, for example, EDX, Coursera, they have several great courses there. Why this is important? Because you saw in the beginning that data science is the meeting point for computer science, mathematics and statistics, and business and domain knowledge. So we need to have that knowledge to get to understand the basics of machine learning. After that, also in those platforms, you can find very, very good courses. And they are not expensive and they are very comprehensive. Okay? So that's what I recommend to everyone. Just make a research on those platforms. You will find very, very good courses. And of course, you can contact me if you need more detail. I can send you suggestions and links, etc. I will share this presentation after a while, and there is a link for my LinkedIn profile. You can connect, and we can keep talking about that. This is valid for everyone here, okay?
I will not take more questions because I see some people have the belly calling. So there is a lunch starting in a few minutes. I guess you can still ask questions, Angelo. I think you are here to have still a few minutes if people want to ask you some things. Otherwise, thank you very much.
Thank you.